Hello everyone! Our speech is on the radio, and I'm Henry. I'll be doing the history of radio.
I'm Matthew Fairburn. I'll be talking about the science of radio waves.
And I'm Miles Warnock, and I'll be talking about the mechanics of radio.
Henry, you're up first.
Thanks, Matthew. Now, the first thing that I would like to talk about is the discovery of electromagnetism. The first major time period in the invention of what we now know as the radio took place all the way back in 1864, when the radio hadn't even been discovered yet. The first important figure in the invention of the radio was James Clerk Maxwell, who was the most famous for suggesting the theory of electromagnetism, which suggested the existence of invisible waves of energy, as well as the theory of electromagnetic waves. These theories led to the creation of Maxwell's equations, a set of equations created by Maxwell in order to explain how electricity and magnetism are one and the same, and that electromagnetic waves are a representation of that energy. The next main influential figure involved in radio waves was David Hughes, who was the first ever person to artificially produce radio waves. In between the years of 1879 and 1886, Hughes was able to wirelessly transmit signals between points spanning up to 500 yards. According to Britannica, the observed effects were attributed to induction by other scientists, but Hughes disagreed with this theory, although he did not suggest his own. It was only until almost 15 years later, long after the radio had already been invented, when it was realized that the wireless transmissions produced by David Hughes were not due to conduction, but radio waves. Next is Heinrich Hertz, who is responsible for being the first person to officially prove Maxwell's theories, showing that electromagnetic waves, including radio waves, were real. When it was first suggested that he look into Maxwell's theories in 1879, he believed that building an apparatus capable of conducting the experiments would be close to impossible. But while conducting a different experiment involving two metal components, he observed that energy seemed to jump between them. When energy was applied to one, the other would spark. This gave him the idea of how to build his apparatus in order to test Maxwell's theories, which he was able to do between the years of 1886 and 1889. When he conducted experiments proving that energy waves were directly related to Maxwell's findings, thus proving his theories correct. The next major part of the radio's development was the patent war between Nikola Tesla and Marconi. Nikola Tesla was a person who invented many of the components responsible for the radio's invention, which he had patented in 1900. However, he did not invent the radio as a device itself, with that honor falling to inventor Guglielmo Marconi. Marconi patented his radio transmitter device in 1904, and according to Public Broadcasting Service, but Tesla's calm confidence was shattered in 1904, when the U.S. Patent Office suddenly and surprisingly reversed its previous decisions and gave Marconi a patent for the invention of radio. This was seemingly a mistake by the Patent Office, as the patent included multiple inventions already patented by Tesla and had been rejected multiple times for this reason. Although Tesla attempted to fight the patent in court, he was forced to concede due to a lack of funds and died in 1943, right before Marconi's patent was finally revoked. Now, the next thing that we're going to be talking about is the science of electromagnetic waves. Matthew?
Thank you very much, Henry. Now, what exactly is a wavelength? How does it work, and why does it matter? A wavelength is normally defined by the distance between two crests on that wavelength. Rather, the peak of the highest amplitude in that wavelength, which is the distance between the median and the crest. The smaller the wavelength, the higher the frequency, determining whether if it will be a radio wave, a gamma wave, X-ray, or a microwave. Radio waves are the largest wavelength in the electromagnetic spectrum, spanning from a football field to our whole planet in length. Heinrich Hertz proved the existence of radio waves in the late 1800s He used a spark gap attached to an induction coil and separate spark gaps on a receiving antenna. When waves created by the sparks of the coil transmitter were picked up by the receiving antennas, sparks would jump its gap as well. Hertz showed in his experiments that these signals possessed all the properties of electromagnetic waves. Radars, radios, even your microwave oven uses radio waves to properly work. The Wi-Fi that carries data through your house, work, and school all rely completely on radio waves. But how does it work, and what data does it carry? Today, all radios use sine waves to transmit information. Even back then, sine waves were used to transmit simple Morse code messages. A sine wave transmitter narrows this band down to more specific frequencies which can effectively reproduce complex information like audio streams, video and internet data. The narrow frequency band also allows many transmitters to operate in an area without interfering with one another. But how do you encode information onto a radio wave? A simple way to do that is called pulse width modulation, or PWM, where one would turn the wave on and off in a Morse code pattern. This is how signals are sent to radio-controlled clocks. Another method, known as amplitude modulation, or AM, where the amplitude or height of a wavelength changes as the peak of the wavelength changes up and down. The program signal travels from a control board to the transmitter, either by a wire or by a special beam of radio waves. High-powered transmitters are generally far away from the studio, at the site of transmitting antenna, the device that sends radio waves through the air. A method that is a little more efficient is called frequency modulation, which is a little more resistant to static, where the frequency would be pressed down, stretched back out. This method usually allows a little more fidelity, but a smaller range. Digital modulation is a quite newer method, but has been shown to be unreliable. Digital modulation sends signals that are often weak and unstable. Digital modulation encodes digital information onto an analog carrier signal that provides higher fidelity without any of the typical static. In case of things like wireless routers, digital modulation also allows the signal to be encrypted. This way, the transmitter will only send data to particular devices. However, a digital signal that is too weak will quickly become unstable and fall apart. Audio data will sound scrambled, videos become highly pixelated and low quality. But in the US, over-the-air television has moved entirely over to digital transmission, and many terrestrial radio stations operate on digital antennas in addition to their analog signals. One major factor of wavelengths is frequency. As mentioned earlier, to frequency modulation, the distance between the crest on each wavelength determines the frequency. Whether you turn the radio, you are controlling what frequencies that will pick up and read the data stored in that wavelength. An AM radio operates up to frequencies of 1 million cycles per second. Tuning an AM dial to 680 would read frequencies of 680,000 cycles per second. FM radios operate on wavelengths of 100 million cycles per second. So an FM dial turned to 101.5 would have a reading of 101,500,000 cycles per second. Now, we know a little bit of science behind it, but how does that integrate into the actual radio? Luckily, we have a man to explain it. Miles, please come up.
Alright, so now we understand how radio waves work, but we need to know how they actually travel. Broadcasting usually begins with a receiving device for sound, such as a microphone. The microphone receives data in the form of electrical pulses and then sent into the inside of the radio, where an oscillator will convert the electrical pulses into a wave. My radio here has a very small version of that oscillator, like a little chip inside of it rather than a cube, which might look something like this. Click. Okay, this is usually done, they usually turn it into a wave by either changing the frequency of the wave, speeding up and slowing it down, or changing the amplitude of the wave, changing the height of the wave. Matthew explained these earlier when talking about AM and FM radio. Regardless of with which way the oscillator converts it, the audio is translated into a wave. Now, that wave is then sent into a transmitter. High-powered transmitters are at the site of the transmitting antenna, the device that sends radio waves through the air. Special types of radio waves called microwaves are sometimes used to send the program signal from the studio to a distant transmitter in a narrowly focused beam. So, the wave is turned into both a radio wave and into a microwave. The radio wave is for higher fidelity, nearer, and the microwave is for much farther, but less fidelity. This also allows it to have much greater range overall. Now, once that wave is converted into the radio and the microwave, it's amplified by the transmitter and sent out. Once the signal is out, someone has to receive it. And receiving the signal is a very similar process to broadcasting, just backwards and with one extra step. So, in order to pick up the signal, the radio must be tuned to the same frequency as the signal that we send out. The antenna on top of the radio will be able to pick up thousands and thousands of signals around it, so that the radio has to tune most of them out. According to the How Things Work website, the job of a tuner is to separate one sine wave from the thousands of radio signals that the antenna receives. In this case, the tuner is tuned to receive the 680,000 Hz signal. Tuners work using a principle called resonance. That is, tuners resonate at and amplify one particular frequency and ignore all the other frequencies in the air. So, once I choose a specific radio station that I want to listen to, I can receive that signal, and the oscillator inside the radio will translate it back into electrical pulses again. Those electrical pulses will travel into a speaker and come out as sound. Now, as long as that broadcast is not obstructed by anything like a mountain or the atmosphere, radio can travel as pretty much far as it wants. Now, the transmitting sound is the most obvious function of broadcasting. It's not the only thing a radio can do. Radio transmission is found in the majority of modern technology, from garage door openers, which open your doors with a press, to Wi-Fi, which uses antennas around your house to transmit data all around. Hundreds of devices you take for granted every day are reliant on radio to function. Though you may not have realized it before, the radio is integral to daily life in modern society. Thank you.
Thank you for listening to our speech, and we hope that today you learned a little bit more about the radio and how it works.